So I will be recording each talk and starting from this morning. And now I will mute everyone so we don't have any problems. And good. We have a couple of co-hosts from my team. So Jong, Hakam, and so on. Dennis, if someone is waiting in the lobby, please admit them because I might not be able to do that anymore now. So let me close that. So good morning, everyone. It is my name is Jan Lagervall. I'm at the University of Luxembourg. It is my great pleasure to welcome you all to today's workshop on some very pressing challenges, but also very important developments in modern societies, and how a new material with quite spectacular optical properties can be of great value in supporting these developments and addressing the challenges. We have a very interdisciplinary scope today, with both audience and speakers representing very different fields, ranging from physics and chemistry to supply chain management and circular economy construction of large buildings. So there is a big risk that certain terms will appear that may be very basic for the speaker, but totally incomprehensible to listeners from different fields. And I would therefore suggest that we use the chat in WebEx to ask whenever a term appears that is new to you, but apparently important. But in order to not distract the speaker, I also suggest that the speaker turns off the chat. So I will not have my chat on. Instead, someone else in the audience may be able to answer a question during the talk, and that way everyone can follow. That would be my suggestion. But if you are a speaker, please turn off the chat so that you don't get distracted. So to set the stage for today's workshop and to introduce you all to this new material that is at the heart of today's talks and discussions, I have prepared a talk that will take about 30 minutes and which I would like to share with you now. Today, it seems rather clear that the 21st century will be the time when the physical and the digital worlds, they stop being parallel realities. Instead, they will merge into one mixed physical and digital reality. Now, this is different from the information technology revolution, which effectively required humans to fully immerse into the digital world, largely losing awareness of the physical outside. Now, instead, the digital world is coming to us in the form of self-driving vehicles, drones, and robots deployed in the spaces where humans live, work, and play. Previously, purely physical items are entering the digital world thanks to RFID chips and technologies like this. And propelled by the pandemic, well, now even we are subject to digital gatekeepers when we have to show our personal QR codes at airports, restaurants, and so on. Very central to this development on the digital side is blockchain, which solves a lot of problems in uniquely identifying and tracking digital assets. These assets may represent money. We all heard of Bitcoin. They may represent people or anything else that is worth protecting. In fact, all physical objects are increasingly getting their digital twin representation in the computer network cloud. This is an incredibly powerful concept that opens many doors across very different fields, from finance to fighting climate change by monitoring the true carbon footprint of buildings. But a problem is that a reliable and trustworthy link between the physical and the digital worlds is still largely missing. Several attempts to use these new opportunities failed because criminal actors didn't hesitate to introduce fake digital twins. Now, we believe that the material at the heart of this workshop, cholesteric spherical reflectors, or CSRs for short, they have a great potential in providing that missing link. This is the idea that we want to explore today. And with this talk, I will give you a bird's eye view of what CSRs are and which their properties are and why these properties open so many interesting application opportunities. So first of all, the term cholesteric refers to a particular state of matter called cholesteric liquid crystal. This state of matter is very kind to us because it self-assembles into a very useful structure. Although it is in a liquid state, the liquid state is important because it allows us to process the cholesteric liquid crystal. We can shape it into any shape we want, and then we can turn it into a solid by a process called polymerization, and then it's much more easy to use these objects. This is what the polymerized solid CSRs look like when you look at them using an electron microscope. You can see that they are spherical, hollow shells with exactly one hole in each shell. They're about 1/10 of a millimeter in diameter. If you look at the exact same arrangement of CSRs using an optical microscope instead, in reflection, you see the peculiar properties that are at the heart of their usefulness. From the top of each CSR, you see a central reflection spot, here with a green color. And around the edge of each CSR, you see a pattern of smaller spots, and they have a slightly different color. The pattern reflects the particular arrangement of the CSRs, because those edge spots, they come from optical communication between different CSRs. And those different colors, well, they come from that nice self-assembled cholesteric structure that I mentioned, which gives rise to what is called selective reflection. The cholesteric structure is a helix, as illustrated in this cartoon, and that helix, like a corkscrew, has two important consequences. First, like any helix, it is periodic. And that means that also the optical properties of the material are periodic with the same period. So if light with wavelength that is similar to the period enters a material, it actually cannot go through. Instead, it gets strongly reflected. But this happens only for that narrow wavelength range that matches the period. And the effect of that is that the reflected light is strongly colored, which color then depends on the helix period. At the same time, the color also depends on the angle between the light beam and the helix axis. The greater the angle, the more the color is shifted from red to blue. We say it's blue shifted. And when we have this peculiar selective reflection behavior on a spherical surface, some very interesting things happen. So here I have drawn two CSRs next to each other. You see that the helix is aligned radially in the CSRs. That's important. Now, if light enters from above and hits the top of each CSRs, it's reflected right back up because the surface at the top is perpendicular to the incoming light beam. And because the light now enters along the helix, it has the maximum wavelength. The angle is 0. And which means in this example, the light is red. The reflected light is red. But light can, of course, enter a bit to the side of the CSR. And then light doesn't go back where it came from, but it is reflected in a different direction. If the light enters at 45-degree angle, the light is reflected horizontally until it hits the neighbor CSR, and then that CSR reflects the light back to the observer so we can see it. But now remember, this is selective reflection, so it selects a certain color, and that color has now been blue shifted. Instead of red, it has become green, further to the blue, because of the larger reflection angle. This is the reason for those blue shifted spots along the edge of each CSR. In this example, they are green. The end result of this is that CSRs actually communicate with each other by light. And they do so in a way that is unique for the arrangement of the CSRs in that particular cluster. On the other hand, this communication pattern is actually not the only pattern that CSR can generate. You remember maybe that CSRs have a single hole after polymerization. The reason for that is that they are actually asymmetric with a thin and a thick side that you can see here when we look at them from the side. It's the thin side that breaks and forms the hole when we polymerize. So far, what you saw was always light externally reflected from the outside of the thick side of the CSR. But we can, of course, turn the shell around and we look at it from the thin side instead, and then a completely different behavior appears. Now the light enters inside the CSR and it becomes an optical echo chamber that gives rise to these colorful rings. So this Janus-like behavior of CSRs means that if you take a sample with CSRs observed from the thin side, as in this case, you see many ring reflections, but then you flip the same sample over, the exact same sample over, the pattern changes completely. And instead, you see this external cross-communication pattern instead. Why is this interesting? Well, it means that each cluster of CSRs creates a truly unique pattern that depends on how the CSRs are arranged in that particular cluster, and which side faces up and which faces down for each individual CSR. We don't have control of these factors when we deposit CSRs on an object. So that means that we can create a unique fingerprint by coating an object with CSRs. And if we lock the arrangement of CSRs in place by solidifying the liquid that surrounds them, that's easy, we can illuminate with UV light or evaporate the solvent, well, then we have made that fingerprint permanently bonded to the object as a coating, allowing it to be reliably identified. But there is another important feature, and that is that the pattern, in contrast to a fingerprint, a regular fingerprint that we all know, the pattern that the CSR create, it actually depends on how we illuminate the CSRs. So here you see a cluster illuminated from above. That's how I illuminated all the samples that we saw so far. If we instead illuminate from the side, as in this experiment, then we see an entirely different pattern. This is the exact same sample, but you see the appearance is completely different just because we change the illumination direction. This strong shift in appearance when we change illumination is an example of what information researchers call a rich set of challenge-response combinations. This is valuable because it makes it practically impossible to clone a CSR cluster. Because it's not enough to reproduce one pattern, you must reproduce all the patterns produced under any illumination conditions. And these properties of CSR clusters are the reason that they are so interesting for fighting counterfeiting and for distinguishing an original object from a copy. Today, this is a very important challenge because counterfeit and substandard products in other ways are really flooding our markets today. Let me just cite a few lines from this OECD report from about half a year ago that highlight the gravity of the situation. They state the results are a cause for concern. Trade in counterfeit and pirated goods amounted to up to 2.5% of world trade in 2019. If we consider only imports into the EU, fake goods amount to 5.8%. That's 119 billion euro. In nominal terms, in absolute terms, and in terms of its share in total trade, the volume of trade in fakes has remained significant, representing amounts close to the GDPs of countries like Austria or Belgium. So it's significant. And this is a report 2 years earlier from the World Health Organization focusing on the effect of substandard and falsified medical problems, where you can read that in low and middle income countries, 1 in 10 medical products is falsified or substandard. This was before the pandemic, and the pandemic has certainly made this worse. Let me point out that counterfeiting really concerns every sector. this slide shows a couple of examples of what is being counterfeited today, from pharmaceuticals to toys, from clothing to electronics, from pet food to airplane parts and wine. Really, everything is being counterfeited. So what can you do with CSRs in terms of fighting counterfeiting? Well, as I mentioned, we coat the original objects with the CSRs. They adopt a random local arrangement that is then locked in place by curing the binder, by solidifying the system. And note that this refers to the local arrangement. We can still make a large-scale pattern that we can define very well. I will come back to that. And this random local arrangement, it gives the object now a unique, unclonable, and tamper-proof fingerprint. We call this a physical unclonable function, or PUF. The important thing that distinguishes this from many other protection mechanisms, where they're based on trade secrets, is that in this case, not even the producer could make a second copy. And another area, or very related, strongly related area where this becomes really important, is supply chain track and trace, and where CSR labels could be really useful. So modern supply chains are overall complex. As I mentioned, they're exposed to counterfeiting. They lack transparency, and regulation is getting more and more important. So a reliable serialization and track and trace solution becomes really, really important. And the solutions we have today, like QR codes, holograms, barcodes, and so on, serial numbers, of course, well, they can be broken, they can be copied, they can be removed. If you make the QR code using CSRs, you can use the unclonable aspect when you read at the close-up pattern upon near-field readout to make sure that this QR code cannot be cloned. And at the same time, they become very easily machine detectable and even readable over a distance while being unnoticeable by humans. This is extremely powerful for logistics, in particular when you bring in robots into logistics and automate the system. So how is this possible? Well, remember that CSRs are spherical, and the spherical shape means that their central reflection spot, the one that was red or green in the previous slides, now it's blue, this is visible no matter from which direction you look. So effectively, our liquid crystal spheres are retroreflectors. This is similar to what you find on many road signs and in high visibility clothing, like certain shoes or safety vests that you may have in your cars. But these are these standard retroreflectors reflect all light. That's why they're so bright. So they're very, very visible. Now, because we use cholesteric spherical reflectors, we have selective reflection. So these retroreflectors operate only in a narrow wavelength band, and we can tune it where we want. We can make it the blue of this liquid crystal, we can change it to red, or we can make it invisible to humans, while it is still visible to robots, by shifting to the infrared, longer wavelengths than red, or to the near ultraviolet, shorter than violet. Both of these are harmless to humans as well as animals. Another very important feature is that the reflection is circularly polarized. This is such an important property that I would like to say a few words about this. So this is actually the second key consequence of that cholesteric helical structure. It has a handedness, right or left-handed. The helix drawn here happens to be left-handed, but it can be either way. The handedness of the helix is transferred to the reflected light, making also the reflected light circularly polarized with the same handedness. So what is polarization? Polarization is a property of light that human eyes cannot distinguish. That is important. We cannot tell whether light is polarized or how it is polarized. But it is very easy to make filters that block one circular polarization and let the other one through. Oops, sorry about that. This is exactly what you see when you what is happening when you visit a 3D cinema, because the goggles that you put on, they have a right-handed polarizer in front of your right eye and a left-handed polarizer in front of your left eye. So why is this? Well, in order to see a 3D movie, you actually need to see two movies, one for each eye. So the movie theater actually shows two movies on top of each other, but one is shown with right-handed circular polarized light, the other one with left-handed. And your goggles make sure that each eye sees the appropriate movie. So this selection of a certain circular polarization, that's something we can use as well. Because CSRs reflect only one circular polarization. Which one is determined by the handedness of the cholesteric helix. So if we watch them through 3D cinema glasses, the reflections are visible with one eye, but they're blocked to the other. So we can use this to detect CSR-coded, encoded information very efficiently. So let me demonstrate that. Here we have used CSRs to write 4 letters onto a glass slide. Here it is. And then we take 2 pictures of the scene at the same time. One is taken through a right-handed polarizer, the other one is taken through a left-handed polarizer. Now we subtract them from each other. And this removes all unpolarized components. And that means basically everything, because the world generally is not circularly polarized. The only thing that is left is the reflectors, which you probably cannot see because they were very deep blue. But let me switch from the blue to the white channel, and then you see the information that was encoded there. And you see it with very strong contrast. And that's because we could remove the background. Removing the background in this way makes it very easy for a robot to find critical information without false positive, no matter how visually busy the environment is, like in a supermarket, for instance. You can imagine how useful it would be for a logistics robot to just filter out all the irrelevant information and see just what it needs to see. At the same time, these markers are unclonable because they are made from CSRs. So we can really trust this encoding that we have given it because it can't be copied. So if you make a QR code or a similar computer readable marker using CSR, we create that reliable link to the digital twin that we were looking for in the beginning. This opens a lot of opportunities for securing supply chains. We can show that a product isn't and doesn't contain components that are substandard, fraudulent, or counterfeit. We can show that it was made in a way that doesn't damage the environment, or at least minimizes the damage environment. We can even track the product's carbon footprint through its life cycle because we have this reliable link to the digital twin. Again, if we work together with certifying agencies, we can confirm that this product was not made using child or slave labor. And one thing I haven't mentioned is we can actually make the codes to be sensitive or responsive to temperature, light, or humidity. And then even without the digital twin, the CSR labels can show if the item has been improperly stored. If we can make QR codes, well, we can make any other type of graphically similar marker. And that brings us to the final part of my talk. This is how we can support robots, augmented reality devices, and construction of the built environment that use these techniques using markers made by CSRs. To explain that, let us first look at a video from the leading international robotics company, Boston Dynamics. Don't just pay attention to this funny robot, but look also at these black and white markers that you see all around the lab where the robot is working. These are called fiducial markers. You see, they are on the items that the robot is dealing with, they are on tables, they are on doors. They are extremely useful for helping the robot to make sense of its world, to understand what it is dealing with, how far away it is, what is the angle to it, and so on. The problem with fiducial markers is that, of course, they are black on white. So these standard fiducial markers, they're only used in labs because they are visible and they disturb the environment. But they are really useful. So If we could make these markers invisible to humans, then it could be extremely useful. So our future vision is that we imagine placing these markers on key components, for instance, of a traffic scene like this. But we have tuned the reflection to the near UV or to the infrared. And because we're using the CSR circular polarized reflection, it helps robots interpret the scene because they can filter out all the irrelevant information. And it's important to point out that this does not violate personal integrity because the markers don't tell the markers only tell that a certain component is a tram, it's a cyclist or a car. They say nothing about who the person in the picture is. At the same time, to us humans, well, the scene hasn't changed because we cannot see the markers. So this vision is far into the future because it would, of course, require the whole world to adopt CSR markers as a standard infrastructure. So instead, we currently focus on scenarios where the markers can be integrated in components as they are being built during construction. As this article from November 2020 highlights, robot-assisted construction is actually a very, very hot topic that may be about to revolutionize the industry. It is the perfect target for using CSR markers, and specifically, the perfect tool to work with is what is called BIM, or Building Information Modeling. In BIM, every physical item has its digital twin, and it's already used today in construction. The problem, or let's say the full power of the system, hasn't been unleashed, however, because the physical and digital worlds are disconnected. If every item in the construction would have an invisible marker, then we can provide that missing link. And at the end of life, when the building is torn down, well, the markers will then help proper sorting of the material to different waste streams. This is really important for environmentally friendly deconstruction. So let me show you a movie roughly of where we are today. This is not quite the latest version. This is an early version that these persons from our team and from Holger's team prepared. On the left-hand side, you see a video stream through a left-handed polarizer. On the middle one, you see through the right-handed polarizer, and you can see in the middle there is a square that is orange in the middle and black in the left. And the right-hand video feed shows the subtraction, and you see that the background is really effectively removed. The nice thing is that this works in live video. So as Hakam is moving the scene here, the paper, the sheet holding the marker, the subtraction works in real time. Later in the demo today, you will see live this type of background subtraction applied to actual fiducial markers made using CSRs. So now I talk about robots and really bringing robots into environments where people work, live, and play. And I think many people are probably quite frightened about this idea of robots entering our everyday spaces. But there are many reasons why one shouldn't be frightened. And this article collection from Wired kind of highlights that there are many reasons to embrace robots. Of course, provided that they can be deployed safely, and invisible fiducial markers can really help in that. For instance, small electrical self-driving vehicles and drones working together can be great for the environment. And of course, for disabled people, there are enormous benefits, just to mention a few examples. But let me summarize my talk in this way. There are many items, like jewelry, for instance, pharmaceuticals or medical tests, or nice bottles of wine, for instance, that are precious to us, that we want to make sure that these are original. We don't want to have a fake. So it is very powerful if we can label these with the serialization marker. At the same time, we have environments where robots and augmented reality devices may have difficulties to navigate, but if we put markers, fiducial markers, on those environments, that helps the robots to navigate a lot. So if we can have these markers, that allows machines to do a kind of categorization at large scale, even over a distance, to distinguish that this is not just a door, but this particular door, or this is that particular wine from Napa Valley. This gets even more effective when we do it with CSRs because the robot sees only the markers because they can remove the background. And at the same time, by going close, looking at the individual arrangement of the CSRs, you can check that it's actually this particular original unique marker. So it's not a fake. And that creates that link between the physical and world and the digital twins. But because we can do these markers invisible to the human eye, well, to us, nothing has changed. Everything looks the way it did before. So let me end with the roadmap of where we are. What I have presented to you today is largely the result of a couple of academic research projects from our group and with collaborators. I will show them in a moment. In one of these projects, it was a proof of concept project from the European Research Council. We actually came up with a business plan for a very specific use case, business plan and business model for protecting sustainably produced agricultural products and confirming their origin. We have secured 2 patents and 1 is being filed. Right now, we have several still academic research projects ongoing. There is another proof of concept grant funded by the Luxembourgish FNR. This is conducted in collaboration with an Indian jewelry producer. The aim is to demonstrate authentication of jewelry items. So what's happening now? Well, in this year, a new project is starting where we're actually trying something completely different, and that is to improve medical testing using these peculiar properties of CSRs. But that's still an academic research project. It's still far into the future. But in parallel, we really want to take on these many challenges that remain to scale up this that are not very well adapted for academic researchers. So we want to see the spin-off company so we can really address the upscaling and the many engineering refining challenges that we need to reach in order to bring this to the market. At the same time, we are expanding our collaborations, and that's why we have this workshop. We will be applying to the European Innovation Council, to Horizon Europe Cluster 4, and so on. Let me just end by thanking the collaborators that are currently active on this topic that you see here. They will actually all be speaking at today's workshop. And through the team leaders here, I would like to thank all of the team members who have been really helpful a lot. So I come back to the program of today. We have started with this introduction. The next talk will be given by Rafael Munoz Salinas, who is an expert in fiducial markers, and he will tell you a bit about using fiducial markers and current uses and future trends. Then we have a schedule change. The third speaker, from originally, he yesterday got a very urgent call to something he could not avoid this morning, so he or Holger will speak in the evening. And instead, Danshin will speak after Rafael, talking about the materials challenges that need to be addressed to bring CSRs to the market. Before the coffee break, finally, Gabriele Lenzini will talk about the secure authentication using CSRs in counterfeiting. After the coffee break, at 11:15, we will have a 15-minute demo. That was supposed to be during the coffee break, during the live meeting, but now we will do it via WebEx instead, where we will show you fiducial marker detection and authentication. After the coffee break, Tiziano Bianchi will tell you about how to detect and authenticate CSR images. And then we have Benny Mentin, who will talk about supply chain transparency and what hidden CSR codes could do there. Christoph Odenweit will tell you about circular economy in construction and about dismountable reusable structures and why CSR markers might be useful there. Then we have Matthew Schwartz joining from the US. I believe he's probably still asleep. We have a time zone issue. And he will talk about CSR opportunities in automation in architecture and construction and for augmented reality. Then we have a lunch break, and after that, Gerd Schröder-Tork from Australia will be talking about very similar circular polarization effects, but actually in nature and in structures inspired by nature. So it's kind of an alternative to what the cholesteric liquid crystal I've been talking about today. Then my postdoc, Jon Gung, will tell you about how these CSR shells are being made. I haven't really showed that to you today, specifically for the infrared and ultraviolet range. Then another postdoc, Hakam Aga, will be showing you that we can actually hide the CSRs from human detection, even if they reflect in the visible range. And he will also show you how this polarization-based readout devices work. Then hopefully we will have Jose Luis Sanchez Lopez and Holger Voss telling about the use of fiducial markers in robotics and automation. And finally, I will tell a little bit about the current strategies for upscaling and automating production of CSRs and CSR-based fiducial markers. After the last coffee break, we will then switch to parallel breakout sessions to discuss a few topics that relate to what we've been talking about during the day, and finally meet again in a plenary session to report on the results. So let me end by thanking my team very much, and I will stop sharing my screen with this. And not just to share my thanking my team, but of course also for the funding. This wouldn't have been possible without the funding organizations that you see here. And I think I have very little time left for questions, I'm afraid. So I would suggest that you write any questions in the chat, unless anyone has an urgent question very quick that you would like to bring up. Otherwise, I'm very happy to answer them in the chat during the day. I hope at least that this gave an introduction to the whole topic, and we can then go into the details. So with that, I would like to introduce Rafael. Rafael Munoz is a full professor at the University of Cordoba in Spain. He has mainly focused on computer vision applied to different fields such as medicine, robotics, and augmented reality, and has co-authored more than 100 academic papers, some of which are considered highly cited. In particular, his work on fiducial marker detection has achieved an important impact. Today, he's presenting a little bit of the main topics of his research, and he will focus his talk on fiducial markers' current state and future trends. I will stop the recording now from